very different in their subjects. So we're going to finish our thermochem today. We ended up talking about Q equals MC delta T, and then we talked about calorimetry. So we're going to keep talking about calorimetry today. And remember, we use that equation E equals Q plus W, right? Really simple looking equation, but really difficult math sometimes. So now, let's say if we have, for example, no work done on the system. So if we don't change volume, remember work was negative P delta V. So if we don't change our volume, right, then that means, remember work is negative P delta V, right? That's our formula for work. And I'll go through this again. So if we don't change our volume, that's a 0. So then W is gone. So that means that E is Q, right? So if work is 0, E is Q, energy is Q. And so that's where we also get this Q of a system is Q, negative Q of our surroundings. Remember, heat out of one is heat into the other. So we're going to talk about a bomb calorimeter right now. And a bomb calorimeter is something you may never have heard of, but you've all actually experienced the result of using one. And so let me see if I have a picture of this. I think I do. Okay. So this is what a bomb calorimeter looks like. So what it is so this huge thing, this is filled with water and it's completely isolated. So it's like this, this is like the size of one of the sinks in lab. Like that's how big it is, right? It's pretty big, this bomb calorimeter. And what it is it's filled, you can see it's filled with water. And then there's this like metal, kind of looks like a kid's sippy cup kind of, like a little metal container. And in the metal container is a little tray that's suspended in the container. And this tray has 2 wires that go right up to here. So here's the wires, and then they meet together, and then there's this ignition wire. So what they do is they put the little sample of whatever it may be, and then they screw the cup together, and it's tight, airtight in here, and then they put it into the water, right? So this is airtight, put into the water. And then you hit the ignition button, and it explodes this. Right, and this explodes. Now, what happens is the heat from this explosion goes out into the water. So that means that the Q that's coming out of this, so the heat's coming out, so it's coming out of this, so your Q here is negative to your positive Q here in the water. So you can actually use the temperature change of the water to figure out how much heat came out of here and to figure out what the joules or calories are in this substance. This is how they find out the calories that we eat. So they it's much more scientific now, but let's say they wanted to do this as a donut. You would literally put a sample of a donut right here. And then you would explode the donut. And then you would measure the heat change in the water and you could figure out the calories of the donut. And it's actually really a quite fun thing to do, to just blow things up. And you don't hear anything when it blows up, by the way, because it's in water and this is totally isolated. But when you open it up, it's just charred remains of whatever you put in there. Okay, so the heat capacity of the calorimeter, by the way, is always going to be measured for you. So each calorimeter has its own heat capacity. And that again, that's going to be based on the size and the amount of water, all these things. And it's usually in kilojoules per degree Celsius, but it could also be joules per degree Celsius or joules per Kelvin. You just have to keep an eye on these units, right? These units are going to be what dictate how we do our problems with our units. Okay, so let's look at this example. So in this case right here, so we have 1 gram of sugar burned in a bomb calorimeter. So we put it in there on the little sample tray and we blew it up. The temperature rises from 24 to 28 degrees. So that means that this water was 24 degrees. After we exploded the sugar, it was 28 degrees. So we're going to use that temperature difference to figure out just how many joules or calories, whichever one we choose to do. In this case, we'll do joules, kilojoules, because that's what the constant's given. Just how many joules or kilojoules was produced in this reaction. Okay, so here's the specific heat of the calorimeter. And then sugar, by the way, sugar, here's the formula for table sugar, which of course I would definitely have to give you. And then our temperature initial of our water, temperature final of our water, and then our specific heat of our calorimeter. So we want to find the energy of the reaction, and we want to find the energy of the reaction for burning 1 mole of our substance. So we're going to use Q equals C delta T, the temperature of the water and the heat capacity of the water, to figure out how much heat was produced in the reaction. And then after that, we'll figure out how much was used per mole. And I would give you the molar mass for this one, and you're going to see why you need this in just a second. So in our reaction here, we're going to use Q equals C delta T. Now, a lot of times people are like, well, why don't I use the mass of the sugar? Because remember, we have to use, it's Q equals C delta T of the calorimeter, right? So this temperature is of the water. This is the calorimeter, right? We don't have a mass of our water. If we wanted to use this, we would need Q equals mass of the sugar, specific heat of the sugar, change in temperature of the sugar. We don't have the specific heat of the sugar. We have the calorimeter, right? So we can't use this. We don't have enough. So we're going to use Q equals C delta T, because there is no mass and we don't need a mass. Because again, if you look at this unit right here, you know that we don't need a mass when we look at this. So first thing we're going to do is the Q of the reaction per mole. We need to figure out what a mole is of this. So if we have 1 gram, all we need to do is convert this to moles, right? So it's like 1.010 grams, C12, H12, O11. Here's our molar mass, 342.3 grams in 1 mole. And that's going to give us our moles of our sugar. So that's going to be this one piece of it down here. Now to figure this piece here, again, that's going to be the Q of our calorimeter times the specific heat of our calorimeter times the temperature change in our calorimeter, right? So this here was given at 4.90 kilojoules per degree Celsius. Our change in temperature, again, final minus initial, right? Its final is 28 minus the initial, that's going to give us the heat of the calorimeter, right? That's the amount of heat going into the calorimeter, right? So this is going to be a positive number because the heat's going into the calorimeter. But we want to know the change in energy for burning of the sugar. So remember, the Q of the calorimeter, it's the negative of the reaction, right? So if we want to say this is the reaction, we're going to need to change our sign to whatever we get. We just write negative to show that we're now taking the point of view of the sugar, not of the water. Okay, so I don't remember the numbers here, so hold on. I'm sure I put this here for us. So let's see here. Okay, yeah, here's our moles. So that's this one right here. 2 point, how many sig figs we have? Oh, 4. Yikes. 2.951 times 10 to the negative 3 moles. Right, so that's our moles. Our change in temperature, 3.41 degrees Celsius, final minus initial, right? We just talked about that. Then we plug all this in. So here is Q of our calorimeter, and there's the delta T. And again, this is a positive number because remember, the heat is going into the water. I'll put all this back in 1 second. I just want to show this picture instead of having to draw it, right? So the heat is going into the water. So it's plus Q here, right? It's going out of here. So this is the negative, right? It's going out of the reaction into the water. So our Q right now is positive, but we want to take the point of view of this reaction. So we need to take the negative of it. And so our Q of our reaction is the negative 16.7. And that makes sense because when you burn things, heat is released. So this should be a negative number, right? This is exothermic. Now, that's the amount of energy. But if we want to know the amount of energy per mole, then we use this because this is our Q of reaction. Here are our moles. We simply just divide those by each other. So here's our Q of our reaction right here. And there's the moles that we just calculated. And we get our answer. And again, this should be negative because we're burning something, right? So when you are looking at the delta E and it's of a calorimeter, in a bomb calorimeter, by definition, a bomb calorimeter is blowing something up, which is going to produce heat. So it should always be negative because we're always producing heat. So it should always be negative. Okay, so now the formula, go ahead.
Can you go back to the last slide really quick?
Sure, with the picture?
The one with the, you can go forward a little bit. It's when you start writing the calculations down.
Oh yeah, when I have the delta T right here?
Yeah, that one.
Right here. Yeah. So here's the mole, right? This is the same calculation we did up here. And then I just did the delta T. I actually did it out instead of leaving it in the equation. Yeah. Whichever way you prefer is fine. Is that good?
Yeah, thank you.
Okay, you're welcome. Okay, so any questions on this problem? So make sure you keep in mind when you're using Q equals MC delta T, it all needs to be the same thing, right? So if you're using Q equals MC delta T, you need to be talking about the Q of this mass, the specific heat of whatever this mass is, and the delta T of the change of whatever the mass is. It all has to be the same. Since what was given to us here is the calorimeter, it's the exact same thing. You just leave the mass out. But this is all of calorimeter, right? So just keep an eye on what you're talking about, because the most common mistake here is somebody tries to put this in here, but then uses the specific heat of the calorimeter and then uses the change of the water. They all have to be the same. Same thing when you're using these equations. Okay, so now we're going to talk about enthalpy. Enthalpy is something you may or may not have heard of. So enthalpy is what we call the delta H of a system, or the H of the system. This is just the sum of the internal energy of a system and the product of the pressure and volume. So H is a state function, remember? So it doesn't matter how we get there, it just matters where we end and begin. So H is E plus PV. Now, if you think about this, right, if we're not changing our pressure or our volume, right, so then that goes away. And remember, E is Q, right, Q plus W. And so then therefore you can say that E is Q. Well, if E is Q, then H is Q. It's kind of like, you remember those geometry proofs when you were like in geometry, we're like, if this, then that, then if this, then that. So in general, when we're at a constant pressure and volume, H is Q. So H and E are very similar to each other. The only real difference is for like huge gas reactions, which we're not going to do. So for our purposes, H is equal to E is equal to Q if we're not changing our volume or pressure, which guess what? We're not changing our volume or pressure. The only time we change our volume or pressure, right, is when we talked about like PV work, or we did the Q plus W's at the beginning. But for now on, and when we do thermodynamics, we're going to assume we're not going to change our volume or our pressure. And so then these are interchangeable to us. Okay, so just as a quick reminder, exothermic and endothermic. So remember, heat released, exothermic. Heat absorbed, endothermic, right? So if you use like, if you ever go into the mountains or go skiing and you get those little hot packs, right, and you shake them up, those are these iron filings, and they oxidize and they have an exothermic reaction, which means they produce heat. And then when you put your hands on them, the heat's going out of the little packet into your hands, making your hands warm. And so that's how the hand warmers work. Now, cold packs, most of us have used a cold pack, right? When you get a cold pack, you have to like squish it, right? And when you squish it, there's like, you hear a little pop, right? And so what happens is you have two solutions that are mixing together with each other. And what happens is it's an endothermic process. That means that heat is going in. So when you put your hand on a cold pack, it feels cold because what's happening is it's taking the heat from your hands, right? So that's why it feels cold, because the heat is going from your hands or your arm or your shoulder or your knee or wherever you put your cold pack, or to your head, right? It's taking the heat from your body into the cold pack. And that's why it feels cold, because it's absorbing your heat. Okay, so when we have an exothermic reaction, again, we're taking the point of view of the reaction, and the energy the heat that we're feeling is coming from potential energy of going from reactants to products. So old bonds are broken and new bonds are formed, and the products of the reaction have less chemical potential energy than the reactants. So I wish I had more room to write this, but I will write this multiple times. So if you have this thing called a reaction profile, right? And we've seen this when we had kinetics in Gen Chem. And so what happens is, if you have, here are our reactants, right? We've got to have our activation energy, right? And here's our products. If we look at this, and this is just the reaction, and this is just delta H, right? Heat. The difference here, you can see that is our delta H, the difference between the energy of our reactants and products. And what this is saying is the products of the reaction have less energy than the reactants. Because what happened is the reactants, that energy was released as heat, right? And so you can see that this is going to be an exothermic reaction. The products will have less potential energy in the end than the reactants, because that energy has been released as heat. So if we were going to write a reaction, and I'm just going to do this, we already did this, but I want to do it one more time. A goes to B, heat is going out of, it's being released, right? And so if we did delta H or E or Q or whatever I want to say, this would be negative, right? So if this, let's say this difference was 5 joules, our delta H would be negative 5 joules. This is what's showing that heat's been released. That's an exothermic reaction. Okay, now endothermic reactions are exactly the opposite, right? So you see how heat exothermic is on the outside, on endothermic it's going to be on the inside. Exothermic is negative, endo will be positive. Exo reactants have more than products. Endo, exactly the opposite. Products will have more than the reactants. So for an endothermic reaction, which I don't have any cool pictures for this one, the surrounding temperature drops due to the absorption of energy by the reaction. So heat is going into the reaction. Heat is going into on the entering side of the reaction. In this case, again, old bonds are broken and new bonds are made, and we're going to talk more about this. The products will have more potential energy than the reactants. How do they get more energy? They get this from absorbing heat and then storing it into, or transferring it into chemical energy. So I do not have a lot of places to write this. I'm going to try and do it right here. It's going to be small. Okay, this again is reaction progress. Here's our delta H. So in this case, our reactants will have less energy, less potential energy than our products. And so you can see here, let's again say that this difference was 5. This would be plus 5 kilojoules. That would be our delta H. Plus 5 kilojoules. Again, this plus means endothermic. Heat is going into. Where's the heat coming from? From outside. So if you're touching it and you feel a beaker or a test tube or something and it feels cold because the heat is going from your hand to that test tube into the reaction, right? Or into the beaker. And that's why it feels cold. Now, when we do this again, let's look at these enthalpies and how we can write these. So this is an extensive property, which means that the more reactants you use, the larger the enthalpy is, which makes sense. Think if you burn a match versus a tree, right? It's going to make a difference, right? The amount of heat is going to make a difference. So we can actually calculate this using moles. So this reaction you can see, is it exothermic or endothermic? What do you think, exo or endo for this reaction?
Exo?
Yeah, yes, yeah. Feel free to say it out loud or type in the chat, whichever one. Exothermic, right? Because it's negative, right? Now, for the reaction, this is 2044 kilojoules per each of these. Now, what do I mean? So this is 2044 for 1 mole of CH3, of C3H8, right? So 1 mole of this is 2044. So we could write it like this, or we could write it like this, or we could write it like this, right? Just depends on what kind of conversion unit we need. But let's say we want to talk about it with respect for oxygen, where there's 5 moles of oxygen that produce. So we need 5 moles of oxygen to produce this much heat. So we, instead of, you can see the difference here, instead of it being 1 mole, it's 5 moles. So we use the stoichiometric coefficients in front of the reaction to figure out which one. So if they were going to say, like, if we wanted it with respect to CO2, it would be negative 2044 kilojoules is 3 CO2s. Or if it was water, it would be 4, right? So when it asks for the reaction, usually the reaction is going to be talking about the thing that's 1 mole, but it might say with respect to a different reactant or product. In this case, this is propane. So we're combusting propane in this case. So we would say, oh, this is the amount of combustion for a mole of propane because this is 1 mole of propane. So let's practice that. Okay, so we have a problem. How much heat is evolved in the complete combustion of 13.2 kilograms of, here we are with propane again. So they give us C3H8. I would give you this molar mass because it's kind of awful. And so in this case, if we just want to know how much is released, here's how many kilojoules and here's how much we used. So we're just going to use this again as a conversion factor because remember, 1 mole of C3H8 equals 2044 kilojoules. So what looks like kind of a problem that you're like, oh, this looks like kind of a hard problem. It's really not a hard problem at all. When we do this, we look at it, we have 13.2 kilograms. Get rid of my kilograms because let's say you have no idea how to do this problem. You definitely know you don't need kilograms, right? So that's a certainty here. 1 kilogram, 1,000 grams. And then you're like, where do I go from here? Well, C3H8, and somehow I need to get here. So if I used a molar mass, right? Molar mass, that would be grams per mole, right? And again, I would probably give you this molar mass, right? So that's here it is, 44 grams in 1 mole, grams. And then our new conversion factor is right here. Right, one of these goes on the top, the other one goes on the bottom. 1 mole of our C3H8 is negative 2,044 kilojoules. So when we burned 13.2 kilograms of propane, we released the 5th kilojoules. So when we burned that much propane, we released 6.12 times 10 to the 5th kilojoules of energy. So this stoichiometry, right? You've done this 100 times, maybe 1,000 now. It's just this new little piece here, right? So that's how we can use enthalpy in our stoichiometry. And I have this meter for you right here. There you are. Now, let's say you forgot this negative. Combustion. Combustion is always negative. Combustion means burning, exploding, burning. This had better be negative. This is definitely going to be an exothermic process. All right. So if this was a multiple choice and any of them were positive, you can just automatically cross off those positive ones because it's not possible. This is a combustion. You know the answer's got to be negative. Okay. So I'm going to have you try one of these now. By the way, if you don't know, diamond, it's just carbon. All right, so try this one and then we're going to go over it in just a minute. So try this problem right now and we'll go over it in just a minute. Okay, seeing lots of these already, so let's just go through this one. So very similar to the one we just did, just to start, this time we're starting with 1 gram, with grams instead of kilograms. So we just use our grams to our molar mass, and then we use this as our conversion unit, and we get negative 395.4 kilojoules. So again, you could have left this in, you could have gone to joules if you want, but this is in kilojoules, so we'll just leave it in kilojoules. Okay, any questions on this one? Makes sense, should definitely be negative. Right, definitely should be negative because again, burning, exothermic, negative. All right. So now we're gonna go back to our Q equals MC delta T, another one of these. This time we're gonna do it with a solution. which you're going to be doing next week on Beyond Labs. So what if we have a solution? And this, by the way, is like our little homemade calorimeter that we can make. And so what happens in this case is this is like, it's like 2 cups, a little like cork top, a little stirring rod, and a little thermometer here. And again, if there's a reaction, this is supposed to mock like an isolated. So this here is supposed to be like isolated from the universe. So everything that happens in this reaction stays in this isolated reaction vessel, right? So this is supposed to be like super isolated. It's not perfect, but it works pretty well. So any reaction that we have that goes on in here, anything that happens in the reaction, right, it's going to go out into the solution. So it's going to be the negative of it. And so if there's a reaction, let's say reaction to Q goes MC delta T of a reaction, it's the same thing opposite out of the reaction is into the solution. So again, taking the point of view of the solution. Okay, so now let's look at one of these problems. Because before we always had a solid and we were dropping into water. But what if we have a solution? For example, this reaction we've actually done before. You've done it in some chemistry class somewhere. You put magnesium, for example, we did this experiment 4 in 219, which you may or may not have actually done in person. Put some magnesium into some hydrochloric acid. The magnesium bubbles and disappears, right? It disappears. What happens? It creates magnesium chloride and hydrogen gas, hence those bubbles. So when we do this, the water, so we put some magnesium, some hydrochloric acid. So we have hydrochloric acid in here, and we put an Mg. And then the reaction occurs. Well, initially, the temperature of the water was 25 degrees Celsius. That was the water. After this all went to products, magnesium chloride and hydrogen, the temperature of the water was 32.8 degrees Celsius. So now if we assume that, we're going to assume that the most of our solution is water here, that means that we can use Q equals MC delta T. Right? We can talk about our magnesium and our water. So let's try this. Okay, so we have 0.158 grams of magnesium, and it says 100 milliliters of water, of our solution. So our solution is mostly water, right? It's dissolved in water, so we're going to make that assumption. Also, we're going to need the density of water here and the specific heat of water. So when we start this problem, we have Q equals MC delta T of our solution, but again, we can use that information to go to our reaction in our water by it's just the negative of it. So we have to remember, here's what we're talking about. If we're talking about our solution to our reaction, we need to remember this piece right here. And then we're going to combine that with what we just learned if we want to go per mole. So it says, what is the delta H of reaction per mole of magnesium? So a mole of magnesium, how many moles of magnesium do we have? That many moles. Well, we just have to convert that to moles. So all we need to find here, all we need to do is to find our Q, make sure it's in respect to magnesium, and then divide it by the moles of magnesium, and that'll be the delta H of our reaction per mole of magnesium, which is what was asked for in our problem. Okay, so we have the specific heat of our solution, so we need to talk about the mass of our solution and the change in temperature of our solution, right? So we have 100 milliliters. We're going to assume the solution's mostly water, and the density of water is 1 gram per milliliter. So that means 100 milliliters of solution, 100 grams, right? So that's one assumption we made, that it's pretty much all water. Now, again, we need to convert this to moles up here. I'm just going to do that now. In the end, I'm going to divide it by moles, which we're good with this, right? Just because we're going to need this in the end. I also need my change in temperature. Remember our temperature, final minus initial, so 32 minus 25. And this should be a positive number because we're talking about our water, right? Heat went into our water, so our water should increase in temperature. Okay. So now we've got, this is all the housekeeping stuff we need, right, for our problem. Now we can solve the problem. Remember, mass of our water, specific heat of our water, change in temperature of our water. That's going to be all of our water. We just need to take the negative of that number, whatever we get, then it's going to be of our reaction, and then just divide by our moles of magnesium. Okay, so here's our 100 grams of water, our specific heat of water, which was given in our problem, the change in temperature, which we just figured out. So when you do this, we get a positive number. But again, remember, that's with respect to the water. The question is asking for it with respect to magnesium, right? Heat went out of the magnesium. If it goes out of the magnesium into the water, we want to take the point of view of the magnesium. We need to take the negative of it, right? So this is specific, this is our water. This is our magnesium. So it's negative. So cross off all our units. Now again, here's our Q of our reaction. And then we just divide it by our moles of magnesium, which we just calculated right here. And again, why do we do that? It's because the question literally asked for delta H of the reaction per mole of magnesium. So that's why we literally are doing that, because that was a question. So here's our Q of our reaction. And then our moles of our magnesium. Now in this case, our answer is in joules because our specific heat, right here, joules, right? So always check your units, double check your units, triple check your units just to make sure, because you've already seen that these specific heats have all sorts of units. They might have joules per mole, kilojoules per mole, joules per gram, joules per gram degree Celsius, kilojoules per mole, Kelvin. They have all sorts of different units. You just need to make sure to know what units to use in your problem. Look at the units that they're giving you in the specific heat, right? That's going to dictate your units of the problem, right? So we did everything in joules, grams, and Celsius, right? Grams, joules, Celsius, because we need to cross them off. The biggest mistakes people make is that they don't pay attention to these units here, and then their answer has the incorrect units in it and it doesn't work. Okay, so that is delta H of a reaction in a coffee cup calorimeter. That's what we call them, coffee cup calorimeters. Okay, now our next piece is going to be reactions using our delta H. Okay, so this is sort of similar like we did in the equilibrium, but it's different. There's different rules. So we're going to add reactions and multiply reactions and flip reactions and all of that. But the rules are different. So remember when we did equilibrium, it was like 1 over or multiply? Different rules. This one, whatever you do to the reaction, you do to the delta H. So if you multiply the reaction by 2, you multiply delta H by 2. If you flip your reaction, you flip the sign of delta H, right? If you divide it by 2, you divide delta H by 2. Now, what do I mean by that? So let's look at these. So when a reaction is multiplied by a factor, you do the same thing to delta H. So whatever you do to the reaction, you do to the delta H. So for example, here's a reaction, carbon plus oxygen makes carbon dioxide. If I multiply this reaction by 2, I multiply my delta H by 2. So it's easier than the equilibrium, right? Whatever you do to the reaction, you do to the delta H. If you flip your reaction, so you see here again, here's our normal reaction. I flipped it. I made it go the other way. So I flipped the sign of my delta H. That's it. So much easier than we did with equilibrium. Whatever you do to your reaction, you do to your delta H. But we can also add them like we did with equilibrium. But again, if we add reactions, we just add delta H's. So we have here, this is what we call Hess's law. So for Hess's law, what it says is that the enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. It means we can add individual reactions, enthalpies, to get to an overall reaction enthalpy. So if we, for example, have two different reactions and two different enthalpies, here's one reaction, here's our second reaction. If we want to know the overall reaction or the third one, we can just add them. So I think the easiest way is to look at this. Okay, so here's two reactions given. As you can see, they want to know the delta H for this reaction. So what we're going to do, in Hess's law, what you do is you rearrange these reactions to make them look like this reaction. Right? Now, you could multiply, divide, flip, all sorts of things. So if we look at this one, we see here in our overall reaction, there's a Cu and there's a Cu. So I'm probably not going to flip this one, right? Maybe though, maybe I might flip this one. Let's look at, let's find one that's only in one place. So here's CuCl, all right, CuCl2, uh-oh, look at this CuCl2. So the only place I'm finding this CuCl2 is in a reactant. And this is the CuCl2. The only place I'm finding it is a product. I need to flip it. So if I'm going to flip this reaction, I also need to flip my sign. So I need to flip my reaction. CuCl2 goes to Cu plus Cl2. I'm going to flip my delta H. I had to because I needed this to be I needed it to be a reactant. That's why I flipped it. Okay. Now let's look at this one. So it's two CuCls. Oh, well, that's already perfect. We might not need to do anything. Let's try it. So I'm just going to write this reaction and not change it. So if I have two Cus plus Cl2 goes to two CuCls. No, I'm not going to change my delta H. Now I'm going to add these reactions, and they should look like this when we're done. So do they look like this? Well, let's see here. Cross this out. There's one Cu. So I've got Cu. Oh, Cl cross out. CuCl2 makes two CuCls. Then all I have to do is add these. 170 kilojoules. And that is the delta H for my overall reaction. So all we're doing is very similar to like we did in our equilibrium chapter, but whatever we do to the reaction, we do the delta H's. And then we're trying to get it to look like whatever reaction they ask us. In this case, this is our overall reaction. And this is Hess's law. And we're going to be using this for a very long time this semester. Very long time. All right, let me see if I have this neater. I think I do. Oh yeah, so much neater. So here's the exact same thing. It's just prettier. And I cross them out. Much prettier. All right, so let's try another Hess's law problem. All right, so this is the reaction we want them to look like. These are the reactions and the delta H's we have. So we need to rearrange those reactions and those delta H's to make them look like this overall reaction. So I think the easiest way to do Hess's law, everybody kind of has their own preference. I try to find something that's only found one place, right? And then try to figure out where it is. Like, for example, if you look here, here's nitric acid. There's only nitric acid found one place here, and it's half, right? So that means what I'm going to have to do with this one, because I need this to be a 2, I'm going to have to multiply this one by half, because I need half of them, which means I have to multiply this by 1/2. I'll do it on the other side to make it easier. And then let's look. NO. Let's see here. NO. Do I find a lot of NOs here? I need one NO here. Oh, but I have it here and here, right? Oh, that one's going to be a little hard. We'll wait for that one. Let's look at another one. Oxygen needs to not be present. Like, period. We can't have any oxygen. So right now, we've got oxygen here and here. So we need to decide, one of them's got to flip. All right, so let's look at another one. Look at here. NO2. Oh, but this NO2 is the only place found. It's a reactant here in a product. And it's 3 and 2. Okay, so if it's 3/2, that means I need to flip this one, right? So I need to flip it. And get that 2 away because I need 3. So flip it and multiply it by 3/2. Right, so you see, this is kind of how, and again, then what I would do is I would rewrite all of them, right? So let's look what we did with the first one. Oh, I did times 1.5. It's the same thing as 3/2, right? And I flipped it. You can see I flipped the sign. And then I rewrote the equation. Some people don't rewrite the equation. I think that's a mistake when you don't rewrite the equation, because you don't know if your answer is right until you add your reaction together. Here's what we did the second one. And then with the third one, we can look here. Let's see here. Our N2 is going to need to fall out, right? Because there's no N2 here. So if we look here, we have N2, we're going to have one N2 here. We also need our O2 to fall out. So I'm going to flip this one, because then I can get my N2 to cancel out and I can get the O2s to cancel out. And then I'm going to just pray my NOs work. There's just too many NOs for me to keep track of right now, so I'm just going to hope they work. So I'm going to flip it. So we rewrite all of our equations with whatever we did to them, and then we add it. If it adds to this overall reaction, we've done it correctly. So whatever we do the reaction, here it is, all written down. Cross off everything. There goes all those O2s, which have a bunch of fractions in them. Oops. And indeed, it worked. We got to our overall reaction. So this is the delta H of our overall reaction. So there's a lot of different ways you can do this. It's whichever one you like best. Just remember, whatever you do to your reaction, you do to your delta H, right? And this is Hess's law. You know if your answer is correct, because when you add, your overall reaction and the reaction that you received should be exactly the same. That's how you know if your Hess's law is correct. Okay, now the next thing we're going to talk about is, again, enthalpy, but we're going to talk about what standard means. So we're going to use the word standard a lot in this class. In Chem 229 and in organic, standard always has this little symbol here. That means at standard conditions. Now, it's a little bit different than you learned in 219 because at standard, it was 1 atmosphere, 0 degrees Kelvin, but we do everything at room temperature. So standard here is a little different. So standard is usually 25 degrees Celsius when we're talking about room temperature reactions. It's still 1 atmosphere pressure, and concentration is 1 molar. 1 molar. in the exam, this really gets people in exam 3. When you see this, this means 1 atm, 1 molar, 25 degrees Celsius. That's what that symbol means. That's what standard is. Okay. Now, the standard enthalpy of formation is the enthalpy change for the reaction to form 1 mole of a pure compound from its elements. So the delta H of a pure element is 0 in their standard state. Okay, so I'm going to show you some delta H's of formations so you can see how this works. So here's a huge table of delta H of formations. And you can see these are all going to be in kilojoules per mole. So let's look at oxygen or water. Let's do oxygen. So you can see here, oxygen in its standard state is a 0, right? A standard state, the delta H of formation is 0. And you can see here, here's ozone, which is an allotrope, is 142. Let's look here, what's the water? Here's water gas, negative 241, water liquid, negative 285. We're going to talk about why they're different, right? That has to do with entropy, and we're going to be talking about that one. Let's look at sodium. Sodium solid, 0. Sodium gas, 107.5. Okay, so whenever we're doing a standard enthalpy or looking at a delta H of formation, this is what we're talking about, and this is the amount of energy it takes to form 1 mole of any of these things. And there's some rules when we write these reactions. So again, oops, sorry. So the reactions of the elements in their standard state, again, is to form 1 mole of a pure compound. If you're not sure what the standard state is, find it. It's in the appendix of your book. It's always 0 at a standard state. And again, there can be fractions, because remember the definition is this: to form 1 mole of a pure compound. Now, why can it be fractions? Because there's a few rules when you're writing these. Again, first one, the formation reaction between the elements of compounds. So let's say we're going to do CO. The elements need to be in their standard state. So you would have to look and go, okay, what is the standard state of carbon? What is the standard state of oxygen, right? So we go over and we look for carbon. Oh, standard state of carbon is graphite. Standard state of oxygen is O2. So we need to write the formation of CO using those standard states that are 0, which means we need to use graphite and oxygen. Now, remember, it's 1 mole. So this must be a 1, which means when we balance it, we're going to have to use fractions here because we can't change this number. It must be 1. And you can see we have 2 oxygens, so we're just going to put a half here. And this would be how we write the standard state of formation of CO. Okay, so let's try CO2. And then I'm going to have you try and do the next one on your own. Okay, so for CO2, I got you the standard states. So again, we're going to have to make 1 mole of CO2. But again, it needs to be in the standard state. So we look here and we know, well, I didn't give you carbon because I just told you. It's going to be carbon is graphite plus O2 as a gas, because those were both 0, and that's what makes 1 CO2. So this one's pretty easy. This one, not quite as easy. Okay, so I'm going to give you a minute. I want you to write the standard state of this one, of formation. Remember, it has to be 1 Al2 SO4 3. And everything in the reactants needs to be a standard state. Okay, so they all need to be standard state. Okay, so try this one, and then we'll go through it in just a couple of minutes, like a couple seconds. Okay, so let's try this one. So we've got aluminum, sulfur, oxygen. So we need to write the formation using the standard state of aluminum, oxygen, and sulfur. So aluminum, solid is its standard state, right? Anything in the standard state, solid. Oxygen, O2, sulfur's S8. Okay, so aluminum plus S8 plus O2. Those are our reactants. Remember, it needs to add to this. So we need 2 aluminums. We need 4 O's and 1 S, right? Or 3 S's, sorry. I should wrote that backwards. I get right. 3 S's. So 3 S's and we have an 8 S's. So 3/8 to get rid of that. So 3. And then oxygen, you can see we have 4 times 2, 12 O's. That's an easy one to fix, 12, not 4. 12 O's. And so that would be our reaction for the formation. Again, remembering this has to be a 1 here, right? This has to be 1, and it's 12 O's, not 4. I can count. 12 O's, 3 S's, 3 S's, 12 O's, 2 Al's, 2 Al's. So that's how we write formation reactions. And there it is, much prettier. Okay, the last thing that we're going to talk about is a way we can use these formations to find enthalpy. So we just found the enthalpy of a reaction by doing Hess's law. We can do it using these formations also. And a lot of times you're going to have a choice of which way you would rather do it. So when we calculate the standard enthalpy for a reaction, we can use these delta H's of formations. Now, this formula looks a little complex, but it's really not bad. What we do is we just take the sum of the number of moles of the delta H of the formation of the products minus the sum times the number of moles of the delta H of formation of reactants, right? This is sum. N is the number of coefficients, or the moles that we have. And so it's just products minus reactants, right? So just remember, it's all the products minus all the reactants, right? So you need to remember to distribute this throughout. Okay, so let's look at a question. Okay, so here's the question we have here. We have CH4, right? Methane plus oxygen goes to CO2 and water. So what we can do is we can write these formations. And so if you look at what do we have here? Well, oxygen's at its standard state, so it doesn't have a formation, so we can ignore it. So we can write the formation for CH4, which is carbon, is graphite, hydrogen is H2, right? So we can write the formation for that. And then we would write the formation for CO2. So this is carbon, which is graphite, plus, I think I have this on your slide, so I'm not going to write this again. Carbon plus graphite. And then we add these just exactly like we just did right here. Here's the formation again, 1 mole. Here's the formation, we just did that one, 1 mole. Here's a formation of water, again, 1 mole of it. Then we look at the delta H's of formation, right? And so you can see here, methane is 74.6, CO2, 393.5, and water is right here. Okay, so remember, it's the sum of the products minus the sum of the reactants. So I need to flip this one. So I'm going to do Hess's law way first, and I'm going to show you the other way. So if I'm going to use these, and I want it to look like this, CH4 is a product. I need it to be a reactant. So I'm going to flip my sign, flip my reaction. Flipped my sign, flip my reaction. Okay, let's look at our next one. CO2, CO2. We should be good there, right? Let's look at water. Oh, there's only 1 water. I need 2 waters, right? So I need to multiply this by 2. which means I'm going to multiply this by 2 also. There I am and multiplied by 2. Then when I add all of these, I get my overall reaction, and this is my delta H. Okay, so this is using Hess's law, combining it with our delta H of formations. Okay, so this is just like we did before. So we wrote the delta H of formations for every product that's not in its standard state. We didn't have to write it for oxygen because oxygen's already in its standard state. So we wrote the delta H of our formations, delta H of formations. Then we rearranged these equations to make them look like the overall reaction. Whatever we did to the delta H, to the reactions we did to the delta H's, and then we just added it up. So you can do Hess's law. Now I'm going to show you the other way. So here's products minus reactants. And again, it's kind of open to you which way you want to choose to do this. So this is going to be, products minus reactants this time. So in this case, we look at what are our products. So we have, just going to erase this really fast. So if we look at what we're looking at here, so our products are CO2 and there's one CO2, right? So we have one CO2 in our products, right? Plus 2 waters in our products, minus the whole, all of our reactants. So what do we have in our reactants? We have a CH4, one CH4, plus 2 oxygens, right? So then we just look at the numbers that are given on here. So we look at CO2 is negative 393.5 plus 2 times water. It says water gas, 2 times negative 241.8 minus the whole thing, CH4, negative 74.6 plus water is 0, so it's 0. Guess what we get? You get the exact same thing. And so again, I personally think this way is a lot easier, but you can do it either way. You can use Hess's law to get your answer, or you can use products times their coefficients minus reactants. And remember, don't forget it's all of the reactants. Pretty sure I have this neater here. Ah, I do. But no matter what, you end up with the exact same answer. So you can either do Hess's law to get to your delta H of your overall reaction, or you can do products minus reactants. Products minus reactants is a little bit easier. Okay, so let's try this one. And, oops, I'm gonna let you try this one on your own. And you can do it whichever way you want. I'm gonna show you both ways again, but this is the reaction we want. I think I've got all your data down here. So try this one, and I wanna know the enthalpy change. So I wanna know delta H. What's delta H for this reaction? So try either way you wanna do it is fine. I'm gonna show you both ways in a second, but I want you to try this on your own right now. Okay, in the interest of time, well, let's just do it the easy way, right? So the easy way is just going to be, again, products times the moles minus reactants. So here's our products. So it's going to be 4 CO2s plus 2 waters minus 2 C2H2s plus 5 oxygens. Oxygen's already in standard state. This is a 0, so we can ignore it. We just sort of plug CO2, our CO2 gas in. It's right here. So that's 4 times negative 395.393.5 plus 2 times water. Ooh, it's a liquid this time. So we need to make sure we choose the right one. 285.8 negative minus C2H2, 227.4. And I don't have to worry about oxygen because it's a 0. So I just ignore it, right? And then that's your delta H. Again, it's a lot easier than doing the formations. It's whichever one you choose to do. Okay, so I'm going to just go to this slide where it's nice and neat. Here it is. So much neater now. And we get negative 2600.4 kilojoules. Again, whichever way you like, it's fine. This way is just a little bit easier. Okay, so let's try a problem using this and mix it with a little bit of stoichiometry, right? So for our next problem that we're going to do, so we're going to use this delta H of reaction because I'm not going to give this to you, so we have to find it. Now, how do we do that? Here's our problem. How many kilograms of octane must be combusted to supply 1 times 10 to the 11th kilojoules of energy? So we want to get to kilograms of octane, right? This is our goal, kilograms of octane. Well, we don't have a delta H right here, so we have to find our delta H. So therefore, we're going to have to write a balanced chemical equation to figure out our delta H. Now, we can all write this balanced chemical equation. We might not want to, but we definitely can, right? Octane, I would have to tell you it's C8H18. And here's our balanced chemical equation. Just going to give you that, right? So we need to figure out what is the delta H of octane. Well, you can see here, we have 8. We have to look up the value. So we have 8 CO2s, 9 water gases, minus 1 C8H18, and 25 halves of oxygen, but it doesn't matter because oxygen is 0, right? And so we just plug those into our equation. So then here's our 8 CO2s, our 9 water gases, our 1 CH18, and again, we ignore water because it's a 0. I mean, sorry, we ignore oxygen because it's a 0, right? And so here is the delta H for 1 mole of CH18, right? So that's the amount of CH18. This is 1 mole. So we have, I'm going to write it up here. There it is, wrote it up there. Now, again, that's for 1 mole of CH18, but how much do I have? We have this much energy. So we want to know how many kilograms of octane that is. So we're going to make a total of 1, I'm going to worry about my sig figs later, 1 times 10 to the 11th kilojoules, right? And I just calculated that there's negative 5,000, I'm looking right here, 74.1 kilojoules in 1 mole of CaH18, right? That's what we just did like a few slides ago, right? That's what that means. And in 1 mole of CaH18, there is, there's my molar mass. I was like, oh, I don't want to add that. I would give you this molar mass. Grams of C8H18. Oh, but this asks for kilograms. Right, there's 1,000 grams in 1 kilogram. You do this, you get 2 sig figs, 2.3 times 10 to the 6 kilograms. So how many kilograms makes this much energy? 2.3 times 10 to the 6 kilograms creates that much energy. And now you can see here, look, you see this one right here? See how this is negative? Well, technically this is negative too, right? Because it was produced. What I did is I just ignored it and it was like, how many my kilograms can't be negative, right? So I knew that these would both be either a negative and negative makes a positive, or you just ignore them knowing that your grams are going to be positive. And because this was released or supplied, and we have that as a negative already. So that's where our sign went for this one. All right, any questions on this one?